Outbreak of the 2019 novel coronavirus has caused numerous casualties. Patients' lives are at risk, mostly owing to lung injury, such as acute respiratory distress syndrome, lung epithelial cell necrosis, and apoptosis led by viral infection cause severe inflammation response, resulting in cell injury in the lung. In short, coronavirus infection induces excessive cell death and inflammation, causes lung injury, pneumonia, and fibrosis, and ultimately acute respiratory distress syndrome. Cell death and its relevance to acute lung injury is well documented in the academia. In one research article, TNF-alpha and key necroptosis modulators such as RIPK1, RIPK3, and MLKL are overexpressed in acute respiratory distress syndrome rat in vivo model. TNF-alpha signaling results in inflammatory response and necroptosis. Herein, RIPK1 is critical, mediating necroptosis and inflammation through forming large protein complex and kinase activity. VRN4 shows strong necroptotic inhibition activity across various cell lines, not only in human-derived cells, but also in animal cells, making it easier to validate pharmacology in murine in vivo models. Next, we confirm VRN4 inhibits NF-kappa B and P38 signal pathway induced by TNF-alpha. This signal pathway is mediated by RIPK1, complex 1 structure formation, in which RIPK1's ubiquitination plays a key role. Treatment of VRN4 inhibits P38 and NF-kappa B signaling pathway and polyubiquitination of RIPK1 accordingly. When fibroblast gets activated by TNF-alpha stimulation, proliferation of fibroblasts increases. Treatment of VRN4 inhibits mitotic activity of fibroblasts induced by TNF-alpha. This finding supports VRN4's anti-fibrotic activity followed by injury. Unlike VRN4, GSK's RIPK1 compound does not inhibit fibroblast proliferation. In a LPS-stimulated acute lung injury in vivo model, treatment of VRN4 led less body weight loss as comparable as dexamethasone. Treating VRN4 reduces various pro-inflammatory cytokine releases and inhibit infiltration of immune cell neutrophil. This finding hints VRN4's therapeutic potential for acute lung injury. VRN4's superior anti-inflammation effect to GSK compound can be attributed to structural difference. Unlike other type 3 inhibitors, VRN4 is designed to form distinctive structural and binding mode. We believe uniqueness in design brings difference in RIPK1-mediated complex 1 formation. ATP competitive assay confirms binding mode differentials, and this will be further validated with co-crystallization of RIPK1 and the molecule. Put together, it is evident that binding mode of VRN4 and GSK molecule are not the same. To conclude, there are two major inflammatory responses mediated by TNF-alpha, NF-kappa B, and necroptosis. GSK molecule only inhibits necroptosis by inhibiting RIPK1 catalytic activity. However, VRN4 blocks both NF-kappa B and necroptosis pathway. Compared to TNF antibody, which are too large to penetrate lung tissue, VRN4 can penetrate into lung tissues to suppress inflammation and cell death at the same time, suggesting its therapeutic potential for acute lung injury with high unmet medical needs.